we talked about freezing point depression. Boiling point elevation works in much the same way. The equation is extremely similar. The change in the boiling point is equal to the molality times the boiling point elevation constant for that particular solvent. So antifreeze is something that we put into our radiator fluid instead of just water, because it prevents the freezing of the water within the engine block, but it also prevents it from boiling because it raises the temperature at which the water boils, and so then it can be effective over a wider temperature range. Calculate the boiling point of a 3.6 molal aqueous sucrose solution. So we need the boiling point elevation constant, which is back on this page. We're looking at water. So here's the normal boiling point, and here's the boiling point elevation constant, so 0.512. So the change in the boiling point is equal to the molality times the boiling point elevation constant. So that's going to be 3.6 molal times 0.512 degrees Celsius per molal. Those units cancel out. Calculator. There's our friend the train. So this is 1.8432. With sig figs, it would be 1.84 degrees Celsius. It's asking, though, for the boiling point, right? So a common mistake is, students get kind of excited because, hey, I got this delta T, and you choose that as the answer, and, well, that's the change, right? So we have to know what the actual boiling point is. It's 100 degrees. And again, it might be helpful to draw yourself a little thermometer. It's like, okay, there's 0 where water freezes, and here's 100 where water boils. And so this is the change for the boiling point. So it's going to be up 1.84 degrees, right? So the boiling temperature for this solution will be 100 plus 1.84, or 101.84 degrees Celsius. 100 and 0 for the boiling and freezing points of water, you can treat those as exact numbers. Any questions? Osmotic pressure is another colligative property. Osmosis is the flow of a solvent from a solution with lower concentration to a solution of higher concentration. And this is the process by which you get dehydrated by drinking seawater, because the water is going to move from the less concentrated solution to the more concentrated solution. And this happens across a semi-permeable membrane. So semi-permeable is permeable to some things and not to others. So a lot of biological membranes are permeable to water, but not to other substances like sugar or some ionic compounds. So what happens here then is the water is moving, and the way I remember which direction it is like, okay, nature wants everything to get mixed and be the same, kind of, right? So the water's going to move in the direction to bring the concentrations closer to each other. So if you take the solvent, the water, out of the less concentrated solution, that makes it more concentrated. And you put that water into the more concentrated solution, and that makes it less concentrated. And it'll keep going like that until they're the same concentration. And that process is called osmosis. So here is an osmosis cell. So it's this U-shaped tube, and here is a semi-permeable membrane that allows water to pass through, but not the other solutes. So here we have an aqueous solution with solute particles. Could be sugar, could be salt, could be all kinds of things. And over here we have just plain water. So what's going to happen is there's going to be a net shift or movement of water to this side. One way to think of it is, well, nature's trying to dilute that concentration, right? It can't bring the solute particles over here because of that membrane, but the solvent molecules can get through, so let's push them over here. Another way to think about this is going through this membrane, you basically are heading towards a dynamic equilibrium. So you have water molecules going into the more concentrated solution, and water molecules also coming out of the more concentrated solution. But this is a special situation because this is building up a pressure, right? As the water moves, we have a difference in height, and so this is the pressure of the excess fluid, and that's what's defined as the osmotic pressure of the solution. The osmosis will occur until gravity pulling down on it forces it to stop. If this wasn't a gravity situation, then what we'd have here is the water molecules going this way. There would not be as many, or it wouldn't be going as fast, because there are solute particles in the way. Whereas the water molecules going from this side to that side are going to pass very easily because nothing's getting in their way. So this difference in water level is the osmotic pressure. Remember when we talked about a manometer with liquid mercury, right? And we can measure the pressure in inches of mercury or millimeters of mercury. We would be measuring this in millimeters of water, and that's a much, much smaller pressure, but it is a pressure. So that's called the osmotic pressure. So the osmotic pressure is the pressure required to stop osmosis. And the equation for that is, this is a capital pi. Capital Pi equals, this is the molarity of the solution times the ideal gas constant times the temperature. We can use molarity here instead of molality because we're not intrinsically dealing with temperature changes. This usually is just, we're talking about at a fixed temperature, so we can use molarity. So the molarity of the solution, the ideal gas constant, and the temperature in kelvins. And if we think about what happens with the units there, so molarity would be moles per liter, and the ideal gas constant would be liters times atmospheres divided by moles times kelvins, and the temperature is in kelvins. So the kelvins cancel, and the moles cancel, and the liters cancel, which leaves us with atmosphere, a unit of pressure. If you try to use the other ideal gas constant, the 8.314 joules per mole Kelvin, your units won't work out, right? So calculate the osmotic pressure in atmospheres of a solution containing 1.50 grams of ethylene glycol in 50 milliliters of solution at 25 degrees Celsius. That's okay. So the equation here is this capital Pi is the molarity times R times T, kind of like Mr. T, I guess. So we need to calculate the molarity. So molarity is moles of solute divided by liter of solution, right? So let's just do these separately. So to calculate the moles of solute here, we have to use the molar mass, right? Because we've got 1.50 grams, and we want to convert that to moles and have the grams disappear. This is our conversion factor, the molar mass, right? And so we have to calculate the molar mass, 2 times 12.01 plus 6 times 1.008 plus 2 times 16. Remember, you should always use 4 sig figs on your molar masses. So 62.068 grams for every mole of that compound. So 1 mole, 62.068 grams. This is going to give me 0.0241. So my mass has 3 sig figs, and I'm going to write down 2 extras. So that's how many moles there are. What's the volume of the solution in liters? So 50 milliliters is going to be 0.0500 liters, or if that's, just a little bit sketchy, 50.0 times 10 to the minus 3 liters, because times 10 to the minus 3 is what milli means. So that's probably a safer way to do it. This one, even when people are moving the decimal point in the correct direction, sometimes you accidentally move it too far or not quite far enough, and you end up with 0.5, which would be 500 milliliters. Okay, so we're going to divide this by 50.0 times 10 to the minus 3 liters to calculate our molarity. So 0.48334 moles per liter. So that's the molarity, that's the first term, 0.48334 moles per liter. And then the ideal gas constant, 0.08206 liters times atmospheres over moles times kelvins. And then we've got 25 degrees Celsius, right? So 25 plus 273, 298 Kelvin. .8 atmospheres. Any questions? Osmotic pressure is something that is very relevant in medical fields. Because when you're giving people intravenous fluids, it's really important that the concentration of particles in that IV fluid is compatible with what's in your cells so that you don't get a lot of osmosis occurring, right? You don't want it to pull water out of your cells. You don't want it to push water into your cells either. 11.8 atmosphere.